Hello everyone, today I'm gonna to make a video for visually impaired persons on the topic of rate law for nucleophilic substitution in square planar chapter thermodynamic and kinetic aspects of metal complexes, book Inorganic. So let's start. Rate law for nucleophilic substitution in square planar complexes. Let us consider a typical nucleophilic substitution reaction in a square planar platinum 2 complex. Platinum ligand coordination number 2 Tx plus Y. It will form platinum ligand, two ligands T and Y plus X, in which Y is the entering nucleophilic ligand, X is the leaving ligand, and T is the ligand trans to X. The concentration of the incoming nucleophile Y is very large compared to the platinum complex PtL2TX. It means that Y practically remains constant. It has been experimentally found that the observed rate law in square planar complexes, rate equals to d by dt of platinum L2 Tx equals to K1 Pt L2 Tx plus K2 Pt L2 Tx into y, where PtL2Tx equals to concentration of the complex formed, Y equals to concentration of the ligand. The equation on the rearrangement becomes rate equals to K1 plus K2 Y PtL2Tx equals to K observed PtL2Tx K observed equals to K1 plus K2 into y. We can represent that equation into a graph, that is y equals to mx plus c. Here c is the constant that is given, m is the slope that is k2. The value of K1 and K2 can be determined by carrying out the reaction at various concentrations of Y. A plot of K observed versus concentration Y comes out to be straight, with K1 as the intercept and K2 as slope. Typical plots of the variation of rate constant K observed for a 4-coordinate square planar platinum 2 complex undergoing substitution by a number of nucleophile Y in a coordinating solvent, that is methyl hydroxide, are shown in the figure. The rate can be rationalized in terms two parallel ways, both involving an associative mechanism. The term K2 indicates direct nucleophilic displacement of X by Y. The reaction is first order with respect to both the complexes and the nucleophile Y. This closely demonstrates the associative pathway, which are similar to biomolecular nucleophilic substitution reaction PtL2Tx plus Y, that is slow step PtL2Tx and Y. PtL2Txy with the fast step PtL gonna to form PtL2Ty plus X. The term K1 represents that the reaction is the first order with respect to complex and is independent of Y. It indicates a dissociative pathway. However, there are strong evidences which suggest that This pathway is also associated due to coordinating nature of the solvent. In fact, the solvent behaves as a nucleophile and competes with the incoming nucleophile, that is why for the platinum complex PTL2TX to form PTL2TS. For the PTL2TX plus S, that is slow step, PTL2TXS. PTL2TXS is fast step, PTL2TS plus X. Further, PTL2TS plus Y, PTL2TY plus S. The rate law for the reaction can be written as rate equals to K dash PTL2TX into S plus K double dash PTL2TX into Y. Since the quantity of the solvent is very large, the concentration of the solvent partially remains constant, and we can formulate it into K dash into solvent equals to K1. Therefore, the equation simplifies to equation. The two associative pathway can be complex. For the PTL2TX, that is slow step, PTL2TS plus X. Further, PTL2TX plus Y form PTL2TY plus X. And for the PTL2TS plus X and plus Y, PTL2TY plus X. The first path K1 represents two-step process in which the solvent S is first replaced in the rate determining step. K1 path follows first order kinetics. The K1 path is completed when the intervening solvent ligand is replaced by X. The second order path is characterized by the rate constant K2. Both the path appears to involve associative activation and A or IS mechanism for each step of either the K1 or the K2 paths are assigned. There is another approach in which the term K1 in the rate law can be visualized. According to this approach, K1 can also arise because of the dissociative pathway resulting in the 3-coordinate complex, which can react further with Y as shown to give the substituted product. Further, we see PTL2TX when X leave PTL2T 3-coordinate complex formed. Further, if we add Y, then PTL2TY will form. In view of this dissociative pathway, the rate law expression cannot be distinguished between an associative and dissociative mechanism. For K1 pathway, this uncertainty in the interpretation of K1 term can be resolved by setting up different experiments. A great deal of evidence has been collected in favor of the associative mechanism through many experiments which are outlined below. The reactions have been found to be occur faster in more nucleophilic solvents. It suggests that the solvent plays an important role. The dissociative pathway should speed up in the presence of sterically demanded ligand. However, in practice, the reaction rates are lowered. It suggests that the reaction proceeds by associative mechanism. Thermodynamic studies also favor the associative mechanism in square planar nucleophilic substitution reaction.